All right, can you guys hear me okay? No? Can you hear me okay? Is that too loud? Okay. All right. All right, so today's lecture, it's almost taking a step back from last lecture, but just covering some basics on induction and recursion. Again, it might be basic, but it's really important to get this right, so I want to spend a little extra time on it. All right, so, but before proceeding, last class I only kind of briefly mentioned some parts about the syllabus. I asked you guys to otherwise read it on your own time, and I'm happy to take questions about it. So are there any questions about it? I can do this again next class. Okay, fine. All right, was everyone able to find the website? Okay, all right, great. All right, so what did we do last class? Right, so we did some algorithms, but we also introduced kind of a lot of more general ideas. So, we started kind of small, talking about search problems, things like binary search, but it also helps us understand some distinctions like just log x versus 2 to the x. And we also did merge sort, which I'm guessing you guys have mostly seen before. But it wasn't really just about merge sort. It was also about, using recursion, how to use it correctly, this principle of divide and conquer, right, as introductory examples, how to analyze it with recursion trees. Okay, and also our first real instance of using big O notation. And then probably this should have been newer for more of you. We even did some sorting lower bounds, which also came with some big omega notation, analogous to big O. All right, so when we were doing merge sort, I was really drilling down on how you would kind of design such an algorithm. I know you guys had seen ultimately the algorithm before, but how do you kind of design it and how do you justify it? And there's really 3 steps. The first step is by far the most important. That's that recursive specification. And this is really just a sentence describing what your algorithm does very precisely. It should say what goes in and what goes out, and it sort of creates a contract for your algorithm. This way, first of all, when you implement it, you know what you're doing. That's always great. But more importantly, when you do those recursive subcalls to smaller problems, right? Okay, I want to sort the first half, I want to sort the second half, or I'm going to call merge sort in the first half and call merge sort in the second half. And you want to really clearly understand what it does, because to some extent you haven't implemented merge sort yet. But we rely on that sentence. Okay? And so we try to implement that sentence, and when we're kind of reasoning about recursion, we're going to try to argue that by induction on the input size, our algorithm implements that sentence. And so when I'm trying to justify or prove that merge sort is correct on some specific instance size n, by induction, I'm assuming that it works on all smaller instance sizes. So in particular, I've already kind of assuming in the proof that I can sort that first half and sort that second half because it's smaller. Okay, and I assume it by induction on n. So that's the connection between induction and recursion. Okay, but so I want to spend a little bit more time on recursion today and really doubling down on some of these themes. Okay, so I'm going to start with like a very simple example, sort of a toy story, just to make sure we're on the same page, and then we'll do more interesting problems after that. So, all right. Okay, so let's say stairs. How do you climb like a big staircase, right? And you want to quote unquote come up with an algorithm for climbing stairs. Like, how do you explain to somebody how to climb a flight of stairs? How would you explain to someone how to go up a long staircase? Sure, Mitchell.
Step on the first stair with one foot, then step on the next with the other foot if you want to do it like a little bit faster, or you could just like, actually, yeah, that's the way you do it.
Okay, so you say, okay, I have to put my right foot on the first step, and then I put my left foot on the second step.
Yeah.
Okay. Okay, so now I've done 2 stairs.
And then continue on until you reach the top of the staircase.
Okay, and then continue on until you reach this top of the staircase. So I think, uh, right. So I think what in that answer that you already kind of recognize that you should not give different instructions for step 3 and step 4 and step 5 and step 6, right? It'd be silly if like you explain to someone how to climb 10 stairs and then they ask for how to do 100 stairs and you have to talk for 10 times longer to explain it to them. That's not good use of anyone's time, right? So, okay, so I guess this is the sentence I wrote, but it's more or less the same. Let's take it one step at a time. Let's say you're at a particular step. Then I was doing it the slow way, so I wouldn't walk as fast. I guess I'm slow. But you put on one step, and then you kind of lift your body and until your whole body is above that step. Now you have 2 feet on that step. Good, you've done one step. And now keep going until you get to the top, repeating that same instructions. Okay, and I'm guessing many of you would have roughly said something similar, nothing special. So what are the key points? So I think the most important part of this description, in particular, is that first sentence, because it recognizes that each step is identical, right? For staircase, that seems kind of obvious, but maybe for a more complex problem, to recognize you have some kind of invariant that repeats, I mean, by the time you do that, you're almost done with the problem. Okay. And, okay, so now, maybe the bold part of this sentence, and the part that might make someone dubious, is the last part that claims that if you keep repeating this step, you'll get to the top, right? And it's like, okay, 5 steps I feel good about, maybe 10 steps I feel good about. Does it really work for 1,000,000 steps or something like that if you're a very nervous person, right? Somehow they programmed this robot so it works for 2 steps, but not 3. Okay. All right. So just as a toy example and to demonstrate induction, I thought that we would kind of pretend to do a proof by induction. At some level, we're not really proving something that's mathematically very formal, so it's a little bit awkward. But just to make sure we go through the motions correctly and we're all on the same page. Okay. So suppose I wanted to prove that short description does work for any staircase of any length. Okay. And I'm going to assume, for simplicity, that one instruction for one step does work. Like if you put one step on one and you put, okay, that'll work for one step at a time. So I'm really just focused on proving the part that it'll extend to all staircases. Okay, I want to prove that these instructions will work for staircases of any length. Okay. All right. And given that we're not really proving a normal mathematical thing, so it's all a little bit awkward. Nonetheless, how do I do such a proof? What's the first step? Okay, say it louder. All right, base case. What would be the base case? Yeah. Going from the ground to the first step. That is the right idea, but actually I'm going to say that's not quite right. In other words, I want to find, okay, the statement is, what we want to prove is that these instructions will work for staircases of any length. And I want to kind of find a base case of that statement, so to speak. Is that? A staircase of length 1. Okay, so a base case is a staircase of just one step. Okay. All right, the base case, there's just one step, and we're not arguing that, we're just assuming that the step, like you said, the instructions will work for one step, and that one step will get you to the top of a staircase of one step. Okay, fine. So we know that these instructions work for any one-step staircase. Again, I realize we're not proving anything too profound here. All right, so now what's the next step towards the proof to show it works for all staircases? Yeah. Yeah, now we're going to look at like a general value of n that's larger than 1. Okay, so in general case, some n greater than 1 stairs. And I really am not assuming anything about n beyond the fact that it's at least 1. So we want to come up with some argument that's not saying, well, for 100 stairs. We want to say, oh, for n stairs. Okay? All right. How might I, again, it's all a little awkward. prove this for the general case. Like what would you write down? I'm assuming you guys, probably most of you would be able to do this if asked to, right? Huh? Hypothesis. Okay, that's a word. What do you mean?
Like the inductive hypothesis, we like would say if there is more than one step, then follow the inductive step of take a step.
Okay, so it's a little, it's the right idea, but I'm going to, we need to articulate a little bit differently because I want to be a little bit precise about some of these points. Okay, so something about an inductive hypothesis. All right, what would be the inductive hypothesis in this case? Okay, perfect. So we're going to assume that the instructions work for any n-1 staircase. So you have that in your pocket. You know how to do 999 staircases, and you're stuck looking at a 1,000 staircase, and you want to prove that it'll work for that too. Okay. So now, how do we just put these things together? We're all roughly dealing with the fact that the whole thing's kind of awkward, and we just want to figure out how to do it cleanly and precisely in a convincing manner. Yeah. Prove that you can always take one more step. I didn't expect this answer. Okay. Prove that you can always take one more step. Okay, I guess. Okay, you could do that, but work with me because we're going to instead work with the. Okay.
We can't take one more step all the time because there may be no more steps.
Also, we might be thinking the same thing, but I want to at least articulate it differently. So we're assuming by induction that I have instructions that work for any 999 steps or for any n-1 steps. And I'm trying to deal with n, and I'm just trying to figure out the words to kind of put it together. Yeah.
So the original algorithm.
Yeah.
Guarantees we can step up. We can step one step.
Okay. All right. So what's going on here? Okay. So the instructions work for one step, right? So I feel like that should have been written here. Okay. This I know. Okay. So I can use the instructions to take one step. Okay, and I feel good about that. Okay, so the instructions work for one step, so I take one step. Okay, and let's say that's clean, that's fine. All right. Now what? Sorry. Scan. Yeah, scan and try to figure out how many steps are required. Well, you kind of know. If it starts with n and you took one step, okay, how many stairs are left? Oh, sorry. Oh no. Oh, don't worry too much. We just go forwards, and yeah, we don't have to worry about three-dimensional or bad stairs or anything like that. Yeah.
So you take one step.
Yeah.
You stand on that stair.
Yeah.
Now there are n-1 left. You already know how to do that.
Ah, okay, good. Okay, so, great. So once I've taken one step, n-1 steps remain. What remains in front of us is an n-1 step staircase. Okay, and by induction, on n, I now know that the instructions work for any staircase of n-1 remaining steps. Okay, so I know that I can now apply the instructions and it works for n-1 by using this principle of induction. Okay, so it's all a little bit awkward, maybe because the example is a little bit awkward because it's not a typical mathematical thing. But I hope that the appeal is clear, because otherwise the argument is very short, right? If you just embrace induction, it's just like a three-sentence thing. You take one step, there's n-1 steps left. By induction, we know how to do n-1, right? All right. So in a more complex situation, this may be a lifesaver. Okay, so that's the basic, metaphor. Fine. All right, so let's go to, this is more fun. I assume you guys all knew how to go upstairs before class. This is a more fun puzzle. All right. Has anyone heard of the Tolerophanoid problem? All right. Well, if you guys know the answers, then don't spoil it. All right. So there's the story is you have like three, I don't know, poles out there, posts. Okay. And on one of them is a stack of rings, and I guess from biggest to smallest up at the top. Okay, I think in the story there's like 64 rings or something, some large number. And what you're allowed to do is take a ring from the top of one post and move it onto another post where it goes on top. Okay, but the rule is you have to maintain this kind of ordering. So you can't put a ring onto a smaller ring, right? So in the first step, I can do something like move this top ring here. Okay. Oh man, it goes behind it? That's so annoying. Okay, it's okay. It bothers me so much. One second. There's a way. This is obviously irrelevant, but all right. Okay, so I can move the top ring to B. Okay, and then I could move the next smallest ring over, but I'm not allowed to put it on B because that's a smaller ring. At this point, I can only move it to C. Okay, and then you can do something like move this over here, or you can move this. Oh no, you can't move it anywhere. So I guess this move you'd have to go like this or something like that. Okay, so that's the idea. You can only move these rings one at a time, and you have to kind of keep the order within each post. Okay. All right, and the question is it possible to move all n rings from A to B because they are kind of conflicting with each other, right? You're kind of restricted in your movement, and if so, how? Okay. So here is an instance with 8 rings, so it's not that many. Does anyone see how to do this? Like I've asked you, where should I move the first ring? I mean, obviously this ring has to move first, right? Where would it go, for example? Yeah.
We could do this inductively. So if it's just one ring, then we always do it. Let's say there are n rings. Let's say we can do n rings, and now we are at just one. So the top n rings we move somewhere else. The bottommost one we move somewhere else, and then we move them back.
Okay, that's the right answer. Did you already know this?
I just thought like.
Okay, excellent. Okay, so all right. So what makes this tricky is that if you did take the kind of direct approach and you thought to yourself, well, where do I move the top ring first, right? Here's maybe a natural thought process for many people. Okay, a top ring, I don't know, maybe I'll try moving it here, and then this has to move here, and then it's a little bit easier if I'm doing it so you can visually see it, but then and you move this here, but you imagine trying to run through that in your head, right? And it's obviously getting more and more complicated. And at some level, if you thought in terms of where does the first ring go, it's actually quite tricky to try to balance all the complexity and try to imagine everything working out. But what was suggested is, well, okay, let's do it slowly. We'll get the suggestion will come out naturally. All right, so let's try to do this recursively then, okay? And if I was going to do this recursively, what would be the first step? Tower's designing a recursive solution, yeah. Oh, establish a base case. But before even establishing a base case. Sorry? Well, I was thinking of something even more like a conceptual, I guess. No, it's more of like a pedantic thing. Yes, okay. The answer is we need to first come up with a sentence that we're going to try to approve before worrying about a base. It's got to be base case of something, right? Okay, so the first sentence is to come up, I mean, the first step is to come up with that sentence that you're trying to prove. That'll give you some context that'll justify what you're doing. All right? So here the sentence is, I mean, TOH obviously stands for Tolerophanoid, and I've given four parameters n, a, b, c. Assuming that the n smallest rings are stacked up, in order on post A, move those n rings from post A to post B. Okay? And that's what we're going to try to prove, and that's the first thing we establish. Okay, so we could do that thing now if, yeah, the slides were out of order. That's okay. All right, so now we can do the part that you guys were more excited about. Let's actually implement the sentence. Okay, but just clarifying. Okay, all right, now what's a natural first step? Okay, base case. So what would be a base case? One. What if you're really lazy? You could do even better than one. All right, zero. N equals zero. If n equals zero, there's not much to do. Okay, you're just done, right? You just don't do anything. All right. The general case. N is at least one. All right. Okay, good. General case n is at least one. You know all n ring, or you have the n smallest rings stacked up on post A, and you want to move them from post A to post B. Right. What would we do? Oh, it's not necessarily one. We're just looking at some general n that's at least one.
No, but then if you start this with moving it to C, then it won't work.
I don't know. Okay, if I start something, wait, if I start that, okay, well, if I start this, what's this?
I mean, start moving the ring from A to,
If I start moving the ring from A to C, then it won't work?
yeah, for one. If n is one,
Oh, that's true, yes. Yes, okay, if there's only one ring, then moving it from A to C wouldn't work. That's true, okay. But that's just like, well, that feels more like an observation or some example or some counterexample of something we can't maybe do directly. All right, let's be more, yeah.
We can assume that since we're doing it for n, we can assume that n minus 1 can already be done. So we move the n minus 1. We'll assume that it can be moved to the final state and then move the last ring.
Okay, so if I want to move n minus 1 rings from where to where?
To the intermediate state, which would be again of the 1. And then the final ring can be moved from the initial state to the last.
All right, so give me some code. All right, so I want to move n minus 1 rings, right?
Yeah, you can do that recursive. You can call it in a recursive manner.
Okay, so recursive you said, TOH. Okay, and what are my arguments?
So it would be n minus 1 rings moving from the initial stack, which is A,
Okay.
to C, or whichever is the intermediate post.
Okay, well, what does the sentence say? Based on the sentence, what should,
Okay. To C.
okay?
And the final one would be ready state, it would be D.
Okay, great. All right, step one, we're going to recursively move n minus 1 rings to C. Sorry, it's behind the post. Okay. All right, what's step two? Oh, okay, sorry. Glitch in the matrix. Okay.
So now move the last ring from A to C.
Okay. Great.
And then recursively call it to move from n minus 1 to C to B using A.
All right, n minus 1 from C to B with A as the spare post. Okay, and that's how we solve it. Okay. At some level, it doesn't really give you any explicit instructions unless you unrolled the recursion, but it'll work. Okay. All right. So somehow induction just hides sort of all the rules and the complexities of that puzzle. Roughly, just be worried about a base case and doing like one step, and that turns out to be quite easy. You're not thinking about how all the rings are moving and relating to each other. All right. Okay. So that's the same algorithm. Very simple, right? Here, the base case is just encoded in that if n is greater than 0. If n is 0, then you do nothing. Okay. All right. Okay, so, okay, again, I know this is maybe straightforward for you guys, but if I wanted to prove that this thing works and is correct, I know it's sort of implicit in some of the answers that were given out. Nonetheless, let's go through it. Again, how do we prove this? So, some level, I want to prove that our pseudocode implements the sentence, the recursive spec for all values of n. Okay. Again, what are the basic steps we do? What comes first? I think you're saying base? No? Yeah. Okay. Thank you. Oh, oops. All right. Or I guess n equals 0 is what we did, but okay, so n equals 0, that's very easy to check, right? Obviously, you do nothing. I think we feel good about that. All right. Then you move on to the general case, right? And then, what do you say? Yeah, okay. So by induction on n, we assume that these recursive calls are correct and that they will properly move without breaking the rules. So I know that, okay, I'll move the n minus 1 rings over, and I know I haven't broken any rules. And then it's clear that moving that one ring over doesn't break any rules. And then recursively and by induction, that recursive call to move the n minus 1 rings back will not break any rules. So ultimately, you have moved all the rings over without breaking any rules. Okay, but you need to ultimately invoke your induction hypothesis, all right, so that you can just say that sub-recursive call will work. Okay, otherwise, it's not justified. Okay, all right, so, I'm not going to write it out in full, but that gets you to argue that it's going to work for n as well. All right, so nice, very clean, very simple. Sort of a famous example of using induction to really clarify something that might have seemed more complex initially. All right, let me put a twist on this. All right, same question, but I want to make it a little bit harder. My goal now is to move all n rings from A to B with the minimum number of moves. Okay, so now I really want to get the best possible algorithm. Before we came up with an algorithm that works and we proved that it's correct. That doesn't break the rules and ultimately moves the n rings over. Okay. But now I want to argue or try to come up with an algorithm that I can prove is minimal. This question makes sense? I want to get an optimal, like minimum number of ring moves algorithm for the Tolerophanoid problem. I don't want the number of moves. I want an algorithm that's optimal.
We could do a recursive. So if we know we just have one ring, we can do it in one step.
Okay, so one ring, we know how to solve that. That's good. How do you do n rings?
So let's say we can do n rings. Then for n plus 1 it will be 2 times f of n plus 1.
Okay, but why?
So you move n rings in the least number of steps somewhere.
Oh, right. So our algorithm would have taken, our algorithm would have taken like 2 times the running time to move n minus 1 plus 1. And then you solve that recursion. But I want to prove that nothing is better. Or come up with something better. Yeah, so I'm not trying to bound our last algorithm. I'm really just trying to come up with the best possible algorithm. Yeah. Okay, yeah, so we can try to do, okay, we're gonna have to try to do something like induction. Okay, good. And we probably feel good about 0 rings. That's an even easier base case. And also 1 ring we all seem to be pretty comfortable with. Okay. All right, so now what's the first step then? To trying to give an inductive approach to an optimal algorithm. Sure. Okay. I think you guys are all kind of approaching the right idea, but still, to formally do this, because I still want to justify that again, optimal algorithm, right? That's sort of what makes it tricky. What would really be the first step? Yeah. Okay, great. Okay, so change the inductive hypothesis, I think, was a key point, and maybe strengthen it. So really, so here's our recursive spec from before, right? This is our original inductive hypothesis. This is not strong enough to prove that it's optimal. It just argues that it works. So if I wanted to strengthen my argument, I might amend this and do what? Sorry? Just we need one person to say it clearly. Yeah. Yeah, okay, we'll just add this one clause to the end of the sentence saying that it's going to do it with the least number of moves. Okay? And I'll argue that otherwise we don't have to do anything different. Okay, so now we just need to verify that that algorithm we previously did will also do it with the least number of moves, but the first step is to set up the inductive hypothesis correctly. Okay, so I think n equals 0, we feel okay, right? And now let's look at the general case when n is bigger than 0. Okay, I know that in order to move the bottom ring over from A to B, those top n minus 1 rings have to be out of the way. That's the only way to do it, right? So we have to at least move these n minus 1 rings over. Okay? So the time any algorithm would take to get to this stage is at least the time taken by our algorithm for n minus 1 rings. Okay? And then you have to move A to B, right? So that's one more. Okay? And then any algorithm has to move these n minus 1 rings back. Okay? So any algorithm has to do at least the work we're doing. Okay? And by induction, we already are moving the n minus 1 rings with the minimum number of steps. Okay? Yeah. Sure, I think that's what I intended. So any other algorithm has to move the n minus 1 rings over, and we know that we can do it with the minimum number of steps. So we dominate that step. So, okay, sure. Maybe I didn't do a good job, but that's what I intended. Okay. But the key point is just strengthening the inductive hypothesis. Then I'll let you prove something. Okay, the algorithm didn't actually change. Okay. Any questions? All right. Fine. Okay. All right, I have a couple more examples for us. All right, here's kind of a very basic problem. I'm sure you guys all know. It's computing the greatest common divisor. So if I give you two integers, then you want to find the largest integer that divides both of those numbers. Okay. So does anyone know what the greatest common divisor is of 146,740 and 12,180? If I did my math right. I don't know why you guys would be able to figure this out, but any guesses? Silly guesses. Okay. All right, so it's 580. Fine. But okay, these, at some level, this already tells you the problem is non-trivial because those are only like 6-digit numbers, right? The input size is 6, and it already stumps us. All right. Okay. So I thought I'd give you guys a chance, assuming you don't know the answer already, of trying to think of an algorithm, to solve this problem. So I give you as input x and y, and you want to output that largest value q that divides both x and y. I have some hints coming up, but still give you a chance before any hint. Yeah. Sorry? Oh, okay, so you can like factor them into their prime numbers and then take the common primes. Okay, but that's also a lot of work. So I'm looking for something simpler. Prime factorization is tough.
Use the first one minus the second one.
Okay, first one minus the second one. Okay, so if I did x minus y, what does that tell me?
Or do modulo.
Okay, so have you seen this before?
Yeah.
Okay, what was the idea in the back? Okay, so here's an observation going back to Euclid. Okay, that's Wikipedia's picture for Euclid. So let's say x is bigger than y, or x is at least y. Okay, then if q divides x and y, then q will also divide x and x minus y. Okay, and vice versa. If q divides x and x minus y, then since y is x, no. Right, since y is x minus y, then q will also divide y. Okay, so the greatest common divisor of x and y will be the same as the greatest common divisor of x and x minus y. Okay, simple enough. All right, so that's the only kind of trick you need. How do I turn this into a useful algorithm? Yeah. Sure. So what's maybe a nice, elegant, in spirit of the class, what's an elegant word for keep repeating? Okay, we'll do it recursively. And of course, we'll first write a sentence. Okay. All right, so what's a reasonable sentence to set up a recursive algorithm? I'm roughly just asking you to restate the problem. Do you see the xy is? I guess, returns the greatest common denominator of x and y or something, right? Sometimes there's not much to do, but roughly just restate the question. So hopefully, okay. All right. Just to keep things, make the code more compact later on, I'm adding the extra assumption that x is always greater than or equal to y. Of course, it's pretty easy to still use the algorithm. You can just flip the arguments if you need to. Okay. And I'm going to assume x is greater than 0 because if the greatest common denominator of 0 and 0, I guess, is not very well defined. Maybe it's positive infinity, I don't know. But we're just avoiding that, okay? So maybe y is 0, but x is always non-zero. Okay, yeah.
If x divided by x minus y is not a whole number, then y equals x minus y, then
Yeah, we could do that, but or that is one approach. Okay, so if x is a multiple of y, then we just output y, right, as the first step. Although we should probably be worried about y equals 0. So what's the greatest common denominator? No, divisor. What is the greatest common divisor of 10 and 0, technically? What's the largest integer that divides both? 10. But it's not clear what multiple of 0 gets you from 0 to 10. Okay, there's a little awkwardness there, so we should worry about these base cases. Okay. Oh, but anyway, let's just try to implement it. Let's see where it goes. Okay. All right, so GCD XY. All right. Anyone want to throw out a first line? Yeah. You can assume x is greater than or equal to y because that's kind of prescribed in the sentence. I'm assuming that x is going to be greater than or equal to y. Okay, so you say return GCD x minus y. Okay. All right. So if that was our entire code, there's going to be issues. What are some of the issues? Yeah. All right. There's no base case. So like once even if x is equal to y, then you have or like what if y is 0, then you're just getting like xx next time, which probably isn't what you want. Okay. Other issues include x is supposed to be greater than or equal to y, but what if x minus y is, oh. First of all, did I get this wrong? Okay. All right. So all along that should have been y and x minus y, and I read these slides in a bit of a rush. Okay. But even if you did something like y, x minus y here, you should probably still check to see which one's bigger than the other. Okay, but let's start with some base cases. What's a reasonable base case? Yeah. Okay, that's safe. I agree with that. I'm worried about this base case where y equals 0, though. I'm not really sure what x mod 0 is. I actually don't know what x mod 0 is. Yeah. Yeah, perfect. If y equals 0, return x. Base cases are like free, right? Because like they're just a constant number of them and they all take constant time and they just cover your base cases. Okay. Any other base cases or do we want to move on to recursive call? Okay, move on to the recursive call. This is kind of okay, except for that the sentence requires us to make sure that the x argument is bigger than y. So I'm just going to adjust this and write, this will put the max of them here. And again, sorry, it's y and x minus y, not x and x minus y. and I'll put the min in the second slot. Okay. All right, so there then, in terrible handwriting, would be some code. Any other base cases or any other suggestions? Oh, we're assuming x is greater than 0. So we don't have to worry about it. Yeah. Okay, sounds good. I guess I only did the if y equals 0 case, which is maybe a little slower because it won't look for that shortcut, but I think otherwise is still okay. If like y is equal to x, for example, then you'll just get x comma 0 in the next iteration, and you'll get the right answer. So, okay. All right. Again, just for practice, I thought it would be good to try to prove correctness. Okay. All right. So this is not. This is a little bit trickier, I think. All right. So how might we go about proving the correctness of this algorithm? First, what's the buzzword? Sorry. Even before base case. Okay, we'll do a proof by induction, right? Okay. But we have to do a proof by induction on something. So what would that something be? So I want to do proof by induction on some parameter. We got to figure out a good parameter. Previously, there was only like one obvious candidate. Previously, there was some n, and that was like our only choice. So that was easier. N stairs and rings. On x and y. Okay, so x and y is a little awkward because we're juggling two numbers now, right? Which you can kind of do. But suppose I wanted to try to find one number to keep it simple. Otherwise, I have to talk about how to justify two numbers. The minimum of the two. Okay. So if we did proof induction by or induction on minimum of the two. So the one thing I'll point out that's a little bit awkward is that let's say that I don't know x is 101 and y is 2 or something, right? So in the next iteration you'll get 99 and 2. X minus y will be 99, y will be 2. The minimum won't change, right? So that's going to kind of make a proof on the minimum a little awkward because one recursive call to the next didn't actually change the minimum. It'd be nice to find something that goes down with every recursive call. Yeah. X plus y. X plus y does go down, and it's one number, so I don't have to worry about justifying two numbers. You can, in principle, kind of do induction over pairs x, y, but anyway, it's a little fancier. Okay, so we can do a proof by induction on x plus y, right? I think that's what. Okay, good. All right, so great. So now, if we do it on x plus y, what would be a base case? I should show the sentence. What's the minimum value of x plus y that can show up? 1. Okay. And if x plus y is equal to 1, then what do we know? We know that x is 1, y equals 0. We know the greatest common divisor is 1. And we can check, okay, the code would output 1, and okay, we feel good. Yeah, so you'd write that out. All right. In a general case, x plus y is bigger than 1. Okay? All right. So by induction, the algorithm will work whenever x plus y is smaller than the current value of x plus y. Let's say x plus y is equal to some value k, which is bigger than 1. And we assume that, so one thing we can do that's a little stronger than we had done, well, it came up in merge sort. We can assume that the algorithm will work for all values of x and y where x plus y is smaller than k, not just k minus 1. It also worked for k minus 2 minus k minus 3 all the way down to 1. This is called strong induction. Okay, but all those cases have already been proven for you. We just have to do k. Okay. All right, what am I write next? So I'm assuming you guys can all feel good about the correctness of the algorithm. The only tough part or the awkward part is trying to figure out how to put it in words. Right? That's the exercise really, articulating it. Okay, yeah, okay. So let's say so by induction, uh, blah 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 holds for x plus y less than k. Okay, so that's fine. So that's established. I guess I probably should write equal 1 through k minus 1, but anyway, for all values less than k. Yeah, okay, so we basically have, okay, so if we go to here, then we're going to subtract y, right? Okay, so you're saying that means you're claiming that this implies that GCD of the, I guess, max of the thing and the min of the thing works, right? Okay, because x plus y would have gone down. I'll suggest there's just one exception to this. So it does go down by y, but I'm saying sometimes it doesn't go down, even if it goes down by y. You have to still address y equals 0. Okay, so, okay. Okay, so you do have to write, okay, if y is equal to 0, then, and you say, okay, it outputs x, and that's correct because the greatest common divisor of x and 0 would have been x. So you check off and you say, okay, so you say, okay, that's okay. And then otherwise, y is greater than 0, which means that now you know that x minus y plus y, which is the sum of the two arguments in the subcall, is now less than x plus y, because y is now something bigger than 0. And then by induction, the subcall is going to work, and also by the corrected version of Euclid's argument, the greatest common divisor of y and x minus y is also what you're looking for. Okay, so we know that the greatest common divisor of y and x minus y is the greatest common divisor of x and y. And we know that the subcall will work because the sum of the two arguments has gone down. Okay, after checking off that case where y equals 0. Okay, so you have to just be a little bit careful to apply the induction hypothesis correctly. Okay, so of course I didn't write everything out in detail, but I think we see the structure. All right, okay, I want to make an interesting point here. What is the running time of our algorithm? Assume you can do addition, subtraction, in constant time. In the worst case, what's our running time? Okay, big O x plus y, y. Or what would be an example maybe? Or what, yeah, y. Okay, so if the running time is x plus y, the question is why.
So most cases affecting one again and again. So till you reach 0.
Yes, yes. So I agree with that, and I just want to mm, make a sentence that doesn't rely on a clause like in the worst case. I want to make it more kind of clean, I guess, of an argument. How can I argue cleanly that it's x plus y? Okay, so each iteration x plus y, the sum goes down by at least one. Maybe that's what you meant to say, but okay, anyway. The sum of the arguments goes down by at least one, each recursive call. So, it starts at x plus y and eventually gets down to one. That's a base case. Okay, so each iteration will decrease the sum by one, or at least one, and you get x plus y time, assuming you can do addition in constant time. All right. Is that a good running time? Yeah, that's correct. Is this a linear time algorithm? All right, so let's take a vote. You have three categories. One is yes, one is no, one is I'm not voting. Okay. Who's not voting? Okay. All right, who thinks it's a linear time algorithm? Okay, I'd say that's like 66% of the class. Who doesn't think it's a linear time algorithm? Okay. I'd say that's like 31%. Okay, small category of liars. There's 10 of you. All right. Why yes? Most of you said yes. Well, it just looks like it, right? I mean, x is an input, y is an input, x plus y, that's a linear function. Who said no and why? The numbers can be really huge, yes, but it's still x, right? O of x for large x. So there's more to that. You're in the right direction. Sure, but it's at most 2 times x, right? And 2x is also linear. It counts as a linear function. Sorry? Okay. If you actually write down x and y, you only need log x and log y bits in binary notation. So if it is a huge number, an astronomically large number, so it could be the Eddington number or something, right? Which was 10 to the 38 or something. What was it? It was 2 to the 280 or something, right? Okay, that's the biggest number in the world. So your algorithm will take 2 to the 280 time, but your input size is 280 because that's how many bits you need to represent the Eddington number. So compared to 280, 2 to the 280 is a very slow algorithm. In fact, it's an exponential running time. Okay, so if you're actually being very careful, sometimes for numerical algorithms this comes up. Usually we don't care if we're doing like graph algorithms and stuff. We assume the numbers are modest. But for a numerical algorithm like this, we have this bit representation issue where in fact numbers can be expressed so compactly that this what appeared to be a nice running time is actually quite bad. Okay? All right, so our goal is to try to do better. And so here's maybe, I thought it might be helpful to look at a bad case, right? So, okay, when do you realize something like x plus y, right? So if you had, for example, I don't know, x is 101 and 2, then this will be going down by 2 each iteration, right? All the way down to like 5 and 3. And this is just sticking at 2, 2, 2, going all the way down, still 2, still 2. Finally, at the end, it'll switch like that. And this is roughly when the algorithm will terminate. Okay. One thing kind of interesting, so the algorithm is kind of like, it's quite obvious what it's doing, right? It's just subtracting 2, subtracting 2, subtracting 2, subtracting 2. And we were kind of careful, we did it recursively and just did one subtraction at a time. But at some level, you kind of know when it's going to switch, right? You can kind of look ahead and see through what the recursion is doing. And this was in the first suggestion, earlier. So if I kind of wanted to shortcut from beginning to end sort of in one step, instead of just subtracting 2 until you finally get to a smaller number. Yeah. Oh, okay, we can take the modulo. Hopefully I wrote that down. Okay. All right, so if x was bigger than y and r was the remainder, x modulo y. So note in particular that 1 is the remainder of 101 divided by 2. Then I guess the more sophisticated Euclid observation. Okay, that means that x is of the form k times y plus r, where k is sort of the largest integer, so that ky is at most x. Okay. And if some number divides x and y, then that number is also going to divide y and r. Okay. And really the modulo is just shortcutting the subtraction. That's a proof in and of itself. Okay. So, all right, so that's, that gives us maybe a different approach to implementing the algorithm. We can keep the sentence the exact same. We're implementing the same thing. Okay. But now what we've done is we've added this trick, where rather than subtracting, I'm just taking x mod y, which I know is going to be smaller than y. So I don't have to do the max min stuff anymore. It's going to be less than equal to y. Okay. All right, so that's just shortcutting the algorithm. I know that some of we've implicitly proved it insofar as modulo is just shortcutting those steps, but I wanted to reprove this again from scratch because there's a more direct way to do it. Okay, it'll be good practice. Okay, particularly you can do something other than x plus y this time. So if I wanted to prove that this modulo version worked and didn't want to fall back on our last proof, what would be a different parameter that I can do induction on? Y. Okay, so in this version of the algorithm, y does go down. Okay, because the remainder is always some number smaller than y, strictly smaller actually. Okay, so if I'm doing proof by induction on y, what's the base case? Y is 0. I think that is easy enough. If y is 0, you should just return x because that's the definition. Otherwise, in a general case, you assume by induction it works for all smaller values of y. Yeah, okay, well, we'll write it out for the sake of time. But you assume by induction that works for all values smaller than all smaller values of y. I know that remainder is going to be smaller, so that recursive subcall will give me the answer and be correct. Yeah, I think you guys see the pattern. Okay, all right, so this algorithm will also work. But the more interesting part is the running time. Okay. So if I wanted to analyze the running time, and we won't be able to do recursion trees, we'll do some more clever direct thing. All right. I want to try to argue that this algorithm is much faster. Okay. All right. So, I mean, the previous running time of x plus y still holds, because x plus y is going down each iteration. But I want to try to argue that it's going to be much faster. For the sake of conversation, suppose that the x mod y operation takes constant time. Really, it'll take, log x time if you wanted to do a bitwise operation, but I'm really interested in how many kind of recursive subcalls there are. Does anyone see how to bound this? Okay, but why? Okay, so if the answer is something like log x plus y or log x or something like that, something needs to be going down by like a constant factor. And then we're like binary search or over-under game got us a log time. That's because we're eliminating, half of the options each iteration, right? We were chopping off a lot of stuff. So we need to find something like that here. Yeah. Takes at least one number by half. Okay, good. Good. That's actually better than I had, slightly better than I had in mind. Okay, so let's look at, so you're going from X and Y, and that's going to, okay, that's going to Y, and that's going to X mod Y, right? Okay, so you're saying it's going to take one of the two numbers to half. So, okay, so in one case, if Y is less than half of X, that's our number, right? So if Y is less than half of X, then the X parameter has gone down by 1/2. Great, log X. Okay, but what if Y is bigger than half of X? Okay, then the remainder, oh, maybe this doesn't work. Okay. Yeah, is the remainder necessarily small? So, okay, if X was 99 and Y was 50, right? This would go to 50, which is a little bit more than 1/2. And this would go to 49, which is awfully close, right? So in that case, strictly speaking, neither number went down by 1/2. Okay, so that argument doesn't quite work, but we're getting close. Like even take my example, right? 50 and 49. That's actually kind of good. Why? Oh, sorry. The next iteration is going to make a lot of progress. Okay, so if we did get bad luck, right, then actually we know the next iteration is going to do really well. Okay, so let's say we try to take that kind of approach. Okay, so we go from X and Y to Y and X mod Y. Okay, now if this is less than half of Y, then great. The Y parameter went down by 1/2, so I'm just happy in this iteration. But what if X mod Y is bigger than Y over 2? Okay, so what if this value is bigger than Y over 2? The next iteration, this would go to X mod Y. And this would go to some value Z, but what do I know about Z? So it's Y mod X mod Y, but it's Y mod something that's at least Y over 2. This should be at most Y over 2. Okay, because it would be like 100 and 51, so at most 49 can be the remainder. Okay. All right, so every 2 iterations, Y will drop by a factor of 2. So you need log Y iterations overall. All right, good. So that's much better than before. That's assuming that the modulo operation takes constant time. If you actually wanted to worry about the bits, it should take like log X times log Y time. Roughly, you just do log division to get the remainder. Okay, and that'll give you a polynomial running time in the input size. All right, okay, so that distinction will come up again later. All right, so we won't have time to do everything I had planned, and that's fine. I can do at least a little bit because it's pretty and I drew some pictures, and I'll at least expose us to some graphs. Okay, so I had a series of examples set up based on planar graphs. I'll probably only just do one of them. So I'm assuming everyone here is familiar with graphs, but nonetheless, graphs are objects that consist of vertices. They look like points and edges that connect two vertices. Okay, we'll be working with graphs a lot. Planar graphs are graphs that can be drawn, like points and lines representing edges, so that no two edges cross, which is the case here. Okay, so that means it adds some kind of nice. A lot of natural, like things based on maps, are going to be planar graphs because they were originally drawn on a surface. Okay, a lot of geometric things, planar graphs might arise. Okay, but in general, graphs are not planar. So this is a very nice special case with many beautiful properties. So one thing cool about planar graphs that doesn't exist for regular graphs is that once you fix a drawing, then sort of those edges, they create regions in the plane, right? Those white pockets in between. So those regions are called faces of the planar graph. Actually, it doesn't really matter how you draw it. But anyway, so you fix a drawing and then all those regions are faces. That includes sort of the outer region, sort of the things that don't have any edges around it. And that's called the outer face. Okay? That's not necessarily true if it can't be drawn on a plane like this, but if it can be drawn, if it is a planar graph, then you can talk about faces. All right, so here's something really spectacular. It's kind of unbelievable. It's called Euler's formula. All right, so let's let m be the number of edges in the graph, n be the number of vertices, and p is the number of faces. Okay, so I guess in this example, I'm not sure how many. I can't count that high. All right, maybe we'll verify this at the end. The claim, or we'll verify it right now. Oh no, we don't have time. All right, the claim is that n minus m plus p is always equal to 2 for any planar graph, no matter how you draw it or whatever. N minus m plus p is always equal to 2. Okay, as long as it's connected, right? Which is like an absurd claim. All right? Okay, and maybe someone can verify if that's true. If it's, for the example, if it's not true, then that would be, everyone gets an A. Okay. All right, so how might we prove this? This is obviously a spectacular fact. It's unbelievable. How can I prove it? Okay, start from one vertex. So I think implicitly we can prove this by induction on n. Okay, let's start easy. Let's start with n is equal to 1. Okay, so that means there's only one vertex. Now, it is possible in a graph to have self-loops, and it's also well-defined for planar graphs, right? So you could have edges that start and end at the same vertex. They're called self-loops. In that case, this is one region. That is another region. Okay, and then you have the outer region. Okay, so every edge is a self-loop. Okay, so n is 1. M is the number of self-loops. Okay, and the number of faces, every self-loop creates one more face, right? Just whatever it wraps around. Okay, so that means that P is equal to M plus 1. Okay, so let's just plug that in. So we have N minus M plus P. So this was equal to 1 minus M plus M plus 1, which I think is equal to 2. Okay. All right, so that works for n is equal to 1. Great. All right, all we have to do is n greater than 1. Okay. If n is greater than 1, since the graph is connected, there must be at least one edge out there, okay, between two vertices. There's something out there that looks like this. Okay? And maybe they're connected to other things like that. Okay? All right. Now imagine I take this edge and I sort of squeeze the endpoints together. I contract the edge. So I take one graph and I change it by contracting the edge. Okay, so if maybe there were some other edges pointed out like this. All right, so this is going to look like something like two vertices. So that bottom edge is contracted. So those two sides of the triangle now become two parallel edges. Okay. And otherwise, you still have all the other relationships out there. Okay, so this is just like zooming into one small part of the graph. Now, when I do this, what has changed about n, m, and p? Okay. So what happened to n, the number of vertices? It went down by 1. Okay. And what happened to the number of edges? Number of edges decreased by 1. And what happened to the number of faces? Stays the same. Okay. So by induction applied to this smaller graph, which has one less vertex, I know that n minus 1 minus m minus 1 plus p is equal to 2. Because n minus 1 is the vertices in that new graph, n minus 1 is the edges of the new graph, p is the number of faces in the new graph. And then, of course, these two minus 1s cancel out, and you're left with n minus m plus p is equal to 2. Okay, so in fact, this proof is quite easy. Okay. All the great stuff and pictures you missed out on include coloring graphs. Okay, so there are some nice results about coloring planar graphs. You might know there's this famous thing about coloring planar graphs in 4 colors, for which we only have a computer-assisted proof that no one understands. But I would have done a harder version of the problem called list coloring, where you can first do 6 colors. You're going to use Euler's formula for that. And then there's a very nice proof to do better than 6 colors and do 5 colors. Okay, so list coloring is like, the problem is every vertex is given a list of colors that it can take on, and you want to assign colors to the vertices so that on any edge they have 2 different colors. Okay, so, and there's a very nice proof of 5 list colorability. The key idea is to come up with a kind of much more complex induction hypothesis. That would have been the theme of that section. But hey, there's no time, so you can read about it in the notes. It's very nice. All right, thank you very much. I'll see you guys. No class on Monday because it's Martin Luther King Day. So I'll see you guys Wednesday.